So let's talk about this concept that we have in layered hydrostratigraphic media called refraction of streamlines. So refraction of streamlines occurs because when we have a streamline or a flow line that is oblique to an interface, it doesn't just travel straight through. So why is that? Well, we can see that in this construction here. So I've got two different layers, K1 on the top, K2 on the bottom. So hydraulic conductivity of one layer on the top, hydraulic conductivity on the bottom. And we're going to assume, for this case, that K2 is greater than K1. OK? So let's think about what would happen in this case. We have a flow line heading toward this interface. It is at an angle of alpha 1 relative to the perpendicular. And then I've drawn in a bunch of equipotential lines that we know, of course, have to be perpendicular to the flow line. So let's think about what happens to these equipotentials first, right? So what do we know? We always know this. We know the equipotential in the direction of, we know the hydraulic gradient in the direction of flow times the hydraulic conductivity is equal to the specific discharge. And of course, a flow line, that's a specific discharge vector. And so let's think about what happens here when K2 is greater than K1. Well, we know from continuity that QZ in the top layer, so that's the portion of the specific discharge coming in vertically, has to be equal to QZ in the bottom layer, which is the specific discharge coming out the bottom. Why do we know that? Well, if that wasn't the case, then there'd have to be some sort of storage along this interface, because that's just a flow per unit area. So the flow coming in has to be the flow coming out. So we know this is true, and we know this is true. So what does that suggest? So if these two are the same, that means when I'm writing this along the vector. So when since this does not change, if our hydraulic conductivity increases, that means our hydraulic gradient has to decrease, right? So say a hydraulic gradient decreases. Well, to draw a hydraulic gradient that decreases and also maintains head continuity across this profile, it means I have to angle these things, right? Can you see how the only way to get these things to go across and spread them farther apart is to angle them relative to the equipotentials on the in the top layer. So that suggests that this lower specific discharge vector, which has to be perpendicular to that, is going to look something like this. So that's going to have an angle alpha 2 relative to the perpendicular. So that means that my flow line has to bend to accommodate the bending in the equipotential lines. So if you actually work out the geometry of this, what we find is the tangent of these two angles has to be equal to the ratio of the two hydraulic conductivities. So it's actually quite unusual that we actually have to make that calculation. It just doesn't come up a whole lot. But conceptually, it's really useful, because what we see here is that if we have flow coming at some angle to an interface or to a layer, and that layer has a higher hydraulic conductivity, it's going to bend those flow lines around that the higher hydraulic conductivity layer. And so we end up with flow lines that bend toward greater conductivity. So what this might look like if we had multiple layers is something like this. If we have a thin layer and we have a flow line that is coming at that, we have something like this. So if we have K1, K2, K3, and K2 is greater than K1 and K1 equals K3, so in other words, this is a higher hydraulic conductivity layer, then we'll have this thing bend something like that, and then it's going to come out the other side. Right? So this means that in layers of greater hydraulic conductivity, we're going to see more flow. We're going to see more horizontal flow. And in layers of lower hydraulic conductivity, we're going to see flow that's trying to cross those. So the way I remember this is simply flow lines just want to get high. Of course. So just keep that in mind.